I'd like to welcome Gerard Phillips from Arista, who's going to be talking about a network that was pretty impressive. I spent a week there, 2 weeks ago in Wuppertal, where we did an incredible amount of JTNM testing. And this network is something that I think is really interesting to see, a large-scale, multi-vendor, IP-based ST2110 network. So take it away, Gerard.
Thanks for bearing with us. What I wanted to talk to you guys about was the network that we built for the JTNM test event that happened in Wuppertal. So the event is an industry event where vendors get together and they're able to test their 2110 and their NMOS implementations. It's the result of the testing is the ability to kind of put devices that pass the testing can go into the catalogue of devices that pass the testing. What that means is that customers can have a look at that catalogue and work out which bits of kit fulfill the requirements of NMOS and 2110 in terms of interoperability, so they can feel more comfortable and confident about building something for their production, right? So the last one was in 2019, so it's been a while, so you'd hope that 2110 and NMOS have moved on a little bit in terms of adoption and in terms of interoperability and capability. And I've got to say, that is pretty much what we saw. So 45 vendors, 110 participants, quite a lot of kit. Many vendors turned up with many bits of kit. So I am going to talk about the IP network that provided the infrastructure for this event. I'm not talking about the testing event, I think we can talk about that later. I'm going to talk about the network, how we built the network, the best practices we tried to put into the network, and how we configured the network actually. It's more exciting than it sounds. So there's a whole lot of stuff that happens up front. There's a series of kind of expert groups that get together. Those groups agree what the objectives of the testing event is, and they agree how we're going to do the testing. There's an infrastructure group and a testing group. The testing group, pretty self-evident, it works out how to do the testing, what kit is needed, how you get a pass, which parts of which standards are going to get tested. The infrastructure group is responsible for providing the infrastructure on which all these tests can happen. So it's networks, it's DHCP, DNS, BTP, NTP, Wi-Fi access, internet access, you name it, it's it, right? So that's what Arista stepped up to deliver. EView turned up with DHCP servers, DNS servers, the stick in that infrastructure. And Riedel, I've got to say, Riedel did an amazing job hosting it. They provided firewall, internet, and Wi-Fi. I'm going to talk about the design and delivery of the network, the architecture, and the choices we made when we do that. So one of the objectives was to move on the network on which the testing is done. Previously, the testing has been pretty much a big layer 2 network. Everything can see everything. Fixed IP addresses, static IP addressing. Very little of the kind of common functions that exist in a normal network. There was very little, well, in fact there was no DHCP, no DNS, no routing, just great big massive layer 2 network. The objective was to push beyond that to what people should be building and what people are building. So we wanted to do that to make sure that the results were the most useful they could be to customers, because their kit is being tested in a real world scenario. We wanted to kind of use the opportunity to talk about the best practice, make sure people understand what those best practices are. We wanted to build a resilient network that would support the interop and would minimize the size of the failure domain so that any problem devices couldn't take out great chunks of the network and stop the testing. We wanted to make sure that stuff could be tested from anywhere, very flexible. So we pushed on the TR1001 expectations. So we expected DHCP for media interfaces and for management interfaces. We expected DNS to be used to find the RDS servers, the ISO 4 registration discovery servers. We built a layer 3 routed network. We used BGP, so fully dynamic routed network. It's still an IGMP, it's still a dynamic multicast network, still IGMP and PIM, no SDN in there. Unicast was routable everywhere. DHCP, DNS, ISO 4 servers, MTP, PTP, globally available everywhere in a robust fashion. I guess I should say here actually, if there's something I'm not covering or something that isn't clear, just there's not many of you, right? So just shout and let's make it interactive if that makes sense for you guys, okay? Happy to do that. So this time around we built a true amber and blue network, so 2 air-gap networks. Full multicast routing within each of those networks. Full layer 3 attachability, full layer 3 routability everywhere. Big difference this time was every endpoint, the expectation was every endpoint was on its own layer 3 rooted interface. Okay? So what does that mean? It means it's in its own little miniature failure domain. So if that device starts generating bad multicast or has got an IP address of somebody else's device, it doesn't matter. It can't affect anybody else. It's isolated unless it's playing nicely. In the controller and monitoring network, which supports all the services, DNS, DHCP, RDS, NTP, all those things, internet, that network, there's a separate network for that, which was also completely routable from anywhere. So any endpoint could access all the services through either of its media interfaces or any of its management interfaces that were attached. And there was a strong expectation that endpoints would use DHCP and DNS to find the RDS servers. So this was really putting quite a, it's a big ask to expect all the vendors to be able to support this stuff. But these are all the expectations, all the stuff that's in the roadmap for TR 1001. This is all the stuff that makes building a network way easier, because you don't have IP addresses that you've got to manually enter. You're not limiting yourself to not being able to move devices around because if you move it, it's in the wrong IP address. DHCP fixes all that stuff. I mean, it's the way we all work with our phones and our laptops every day of the week. So this really was an attempt to move the industry forwards to use much more, I'm not even going to say modern, much more normal enterprisey IP functionality that just exists. It's out there. You should be using it all. So the physical network was 8 racks of kit. It's a big old event. I was pretty surprised. I'm not going to read out all these numbers. There was a spine and 5 leads in each network. So there's 10 media switches. There was a 4-switch management network. There was a massive move from 10 to 25, if I compare it to 2019. So way more 25 gig interfaces, way more 100 gig interfaces, way more interfaces full stop. It's a bigger network by a long way. And an awful lot more devices were using both red and blue. So there's a lot more amber and blue. There's a lot more devices that are now Dash 7 compliant. So, not an insignificant network. 75 10 gig interfaces, 116 25 gig devices. You could build a fair size studio or MCR or production facility with this network. Okay? The physical network, pretty simple. A leaf and spine on both sides, an amber one and a blue one. Both of those were joined. I think of the management, the spine management device, management one in this drawing. I think of that as a leaf off the media spines, okay? But it's off both media spines. And then hung off that is another 3 devices stretching the management VLANs. So the management network is routable, but it was a series of big flat VLANs. And those big flat VLANs were to enable a main control and monitoring network, which most people were in all the time. And then we provided 4 other VLANs where individual NMOS testing processes took place. So individual test gear would move into an NMOS tested control VLAN if they needed control, if that's where they're getting their RDS form, for example. And they'd be moved in and moved back out again. The majority of the people were playing in the main network. So this, to me, this is a good example of a fairly reasonable network. So you've got your amber, you've got your blue, You can see the GMs are both attached to leaf 5 in both networks. You can see a connection between those two switches, which was to facilitate BMCA, direct BMCA between the two GMs. Those BMCA tests were running all the time. That worked absolutely fine. This is completely standard. It's interesting, we often see networks where the PTP comes in on dedicated PTP leaves. That is absolutely fine, completely happy with that. This is an example, if you like, of overloading the functionality of those leaves. So they're both media leaves, they were the 1 gig audio leaves, and they are the PTP leaves. Now that, some people don't like the idea of overloading, having multiple functions in a switch. That's fine. Equally, if you're looking to save money or be a little bit more compact, this architecture works very well. So it's a media leaf and it's the PTP distribution. Okay, and there was no negative feedback about the architecture, about the PTP, about anything. This network worked really well. It's a network template that you can certainly choose to roll out in production, pretty much. I would make the management network a little bit more robust with kind of dual homing and things like that, but other than that, this is not a bad network. And conceptually, it's the sort of network you see in quite a few productions these days. So, resilient links, multiple links, pretty much between every switch. Pretty robust. Kind of a more contextualized. You can see the management switches is where all of the services hung off. This is what I see, this is what I want to see. So this will be my best practice. So DNS, DHCP, ISO4, RDS, they were all hung off the management network, all routable from anywhere, all very flexible, and could have been built resilient. Could have been built with dual-homed devices and could have been built with dual-home switches, but that didn't have a lot of value to what we were doing. So everyone could get to the internet from anywhere. There was default routes that got you out of the AMBER network, through the management network, and off to the firewall, to the Wi-Fi. So it was a very, very flexible network to be working in. You had availability of pretty much everything from anywhere. We had a mixture of devices that were attached to leaves. Some were attached to leaves, some were attached to spines. My network colleagues get a bit grumpy about directly attaching stuff to spines, but in a single spine device, a single spine architecture, that's completely fine. And for things like multi-viewers, vision mixers, high bandwidth devices, hanging them off a 100 gig spine is a pretty efficient way of doing things, right? They're likely to need a lot of flows, they're likely to have 100 gig interfaces. The spine is where a lot of flows are going to be anyway, so hanging those multi-viewers, vision mixers, the things that consume traffic it's a pretty good way of going, I think. There were, in a production environment, you would probably hang the -7 device off the same port, off the same leaf, but the amber and the blue version. It's nice and simple, it's symmetric, it's easy to understand, it's documentable. In this network, I just put stuff wherever I had a spare port. So there were people who had an amber leg on a leaf and a blue leg on a spine. Sounds a bit wacky, right? Different latencies, different number of hops, in some cases different technologies in the switches in the two legs. Do you know what? People get worried about latency, they worry about these things. Nobody knew, couldn't tell. The only guy that knew was Prim from Fabrics, who could tell me that his packet distribution was wider on one switch than it was on the other. And do you know what? In the really narrow distribution, it's because it was sat on the same leaf as where the sender was, and the one was a bit wider, it was sat on a different leaf to where the sender was. So a perfect example of being able to measure these things, but actually a perfect example of it really not mattering so much. So yeah, I was not surprised, but I was very pleased to discover all sorts of measurements that were happening that told us that actually most of these things are not terribly critical. So how did I configure 16 switches? So there's 16 switches. There's 6 in each media network, and then there's 4 in the management network. That's a lot of configuration. The traditional approach, I don't necessarily mean JTNM, I mean a traditional approach of configuring switches is that you do it when you've got your switches, and you wait for your switches to arrive, then you sit down with your switches, and you sit in front of the CLI, and you spend days and days and days making little human errors, making mistakes, configuring the wrong thing, accidentally changing the management address and discovering you can't talk to it anymore. There's a ton of things you can do that make life difficult for yourselves. And that traditional approach on the scale of 16 switches, it's painful, right? So, and what you don't end up with is any documentation, and you end up with little human errors that you don't really spot, but turn out sometime later, you know, you've got a link that isn't really working, but you didn't spot it. So, and there's another thing that kind of thrown into the mix here. The showcase timing, not showcase, the JSON tested timing was kind of the point at which they asked us to participate, asked me to participate certainly, was beyond the point at which I booked my holiday. So I was already not going to be available for this event. But we wanted to support the event. So we found the switches, we shipped the switches, and I found a couple of colleagues that were prepared to step in for me. But what I didn't want to do was to chuck those guys into this process and have them sit in front of 16 switches. They're not maybe, you know, they're super smart guys, but they're maybe not as media experienced as myself, so there would have been a bunch of lessons that I've already learned that they would have had to learn themselves. I didn't want that. So I took a kind of a software agile network as code type approach. I provisioned these switches at home without the switches long before the switches were available. Okay, so I had 16 sets of config ready to go 2 weeks before this event happened. I used so basically I used an automation approach. So we used Red Hat's Ansible. Ansible is a software automation tool set which is typically used to automate servers. So all of the big cloud guys were using something like Ansible. If your endpoint has got a SSH or RESTful interface, something vaguely standard, the chances are Ansible will be able to talk to it. Now, being able to talk to something is one thing, being able to configure it is a different thing. So what you need is a set of data models that you can use to describe what you want to happen to generate the configurations, and then you want to push them to your devices. So in conjunction with, and one of the reasons why we use Ansible in Arista, in the networking world, is because there are 20 times as many servers as there are switches. And that means there's 20 times as many people configuring servers as there are switches. And so it makes more sense to use that tool set, which is more widely adopted, been tested more, people understand it, the experience is there, than it is to invent something new, right? So we use that because it exists. It's also free. So other vendors are available. Arista's created this thing called Arista Validated Designs, and that is a series of collections that you can use with Ansible, where you can describe in text files how you want Ansible to shunter through the models of the data models and how these get applied. And the back-end process, what comes out of this process is so you start with a set of source files that describe your network in terms that we understand in our AVD collections. Ansible is the tool set that drives all that through. And what you get out the back end of this process is a set of configuration files for switches, okay? So you put in source files, which you can understand, and you get out switch configuration files. So if you use these collections for other vendors are available, then you can build, with very little information, you can build a layer 3 rooted leaf and spine. You can build the PIM subsystem, the multicast, the rendezvous points, PTP boundary to block configurations, all the common infrastructure, DHCP, DNS, what are the host names, what the management interface is. You can configure, well, I configured everything bar everything bar the forward error correction settings on the ports, because I didn't have the time to do that bit. So I configured everything using source files that describe my network. But I could revision control, and I could push through as many times as I needed to get configurations that were in the shape I wanted. I also I took the spreadsheets that the the end users at the event were using to document their devices. We use those spreadsheets, I convert them to CSVs, and push those through a Python script I wrote, and out the back end of that came the configuration files that I could then push through Ansible to give me all of the host ports as well. So I did no manual configuration at all, except, for example, for the layer 3 router stuff, I specified which ports are connected to which, what pool of IP addresses could the system use for those addresses. I configured almost nothing. Generated 16 configurations. Then I went on holiday. When the guys got on site, the guys at Regal had already physically connected the switches together and put the configs on the switches. And you know what? Other than things like people being in the wrong place, or not plugging into the right switch, or the port error correction not being correct, those configs worked out of the box. There was a network running on day one of that event. They hardly had to make any changes to that network. And it was a direct result of automating those processes and not leaving the option of massive amounts of human error in there. So we had very few network configuration issues, very little reliability issues. Testing started at 9 o'clock on Monday morning. The network guys were available to help people test and understand IP the whole way through. There was no kind of having to fix network bugs, because there weren't. I was massively impressed by the whole process. So, typical problems. What did we see? We saw a 25 and 100 gig kind of offer forward error correction at the link layer. If you don't get that configured correctly at both ends, things don't work. So we saw quite a lot of that. That's just like a little bit of fixing as you go along. We saw some interesting IP addressing kind of mistakes, some DHCP stuff that wasn't quite working as expected. These are all great lessons for the vendors to learn in a safe environment. An environment where the network guys can help them understand what problems are. They can go back to their devs, they can fix things, maybe it's configuration, maybe it's just something they've never tried in their lab. We see a lot of this. We see a lot of people who've got the network they're trying with in the lab is one thing, and they've not necessarily tried in a different network. So part of the massive benefit was being able to try it out in a real network that looked like a production network. Some TTL of 0. I don't know if you know what that means. What it means is that as soon as the packet hits the switch, the router throws it away. Okay? Because its time to live has expired. Now, in a layer 2 network in a lab, that'd be fine. But in a proper network, not going to work. Probably the thing that caused the most problem was some guys had brought some kit that had been previously configured to stream stuff to the internet. They created huge streams of unicast traffic directed at public IP addresses. Now, if you kind of remember my network diagram, in providing amazing flexibility, I also provided the ability to stream huge streams of stuff to the internet. So that unfortunately took the management network down for a little while. We found it, we corrected it, probably didn't cause too many problems. So one of the other things that we did provide was thing that helped life with the guys who were checking the network, debugging the network, was we provided some monitoring. So we used a remote instance of our Cloud Vision monitoring tool. We streamed telemetry to that through the internet, and we were able to have kind of live, ongoing visibility of how the network was performing. I think that's one of the things that it didn't contribute to any of the vendors' experience, except that it meant that our guys could more easily leap on a problem that was not necessarily a massive issue right now, but may become an issue. So, for example, we were able to see devices that were having or creating or experiencing bad packets, so drop packets or packets that had errors in them, CRC errors. So we could go and tell the guys that, it might be working, but you've got a little bit of a flaky interface, maybe you need to clean optics or something. Those sorts of things are typically quite useful. So, yeah, I think that's everything I wanted to say, really. It was a great opportunity to see a bunch of kit working in a best practice IP network, and using the automation to deliver that meant I could go on holiday, and I think it genuinely meant a better experience for the participants. So, happy to take any questions.
Gerard, I do have one question, and put you on the spot here. So when are you going to make all these Ansible and Python tools available for the rest of us to use?
But they are available right now. Yeah, sure. I mean, that stuff is all available. We have a GitHub where you can pull down these AVD collections. We've got some training. Reach out to me or the Arista rep and we'll do your demo. Yeah, it's all out there for free. You don't have to do anything, just give it a go.
Well, and let me just state personally as a testimonial, if you look closely enough in this diagram, you can see me sitting in front of with my back to some of the switches there. This network was great. We put a lot of load on it. We had lots of vendors come through. We had lots of different software that was configured and tested on this. I was actually one of the first test stations where we were looking at making sure that people did DHCP and they did IGMPv3 and all the other good things. And once they did that, everything just floats smoothly through. Massive kudos to you. It was a very pleasant experience to be there and not have to worry about the network, just the gear that was attached to it.
Thanks, Wes. I'll tell you what, that's a good question, and it will lead me to, let me just kind of think about this actually. So, I mean, lead times for switches are not great. That's not something we can do much about. It's a thing. But this approach of automating configurations, being able to do it ahead of time, actually that can help you out in, like, you've got a big configuration, big set of switches. Instead of spending 3 months once the kit has arrived configuring those switches, why not use the lead time of the switches to do that stuff up front? So you can create these, you can create the configurations. As I say, all of this stuff is available, it's open source. You can create those configurations, and there are also a lot of tools out there which are also easy to get hold of. There are tools where you can, other vendors are available, right? But Arista has virtual switches, so you can download a virtual switch, you can run a VM cluster, you can run up a network where you build a set of virtual switches that look the same as the network you want to build, and then you can put your configurations on that network. You can verify stuff like all your routing, your BGP, all those other things. You can verify all that stuff ahead of time. And then when you get your switches, you've got the configurations done. You can start the process of testing at that point. Now, some of the other things that are available in Ansible are the ability to do connection testing. So I could have built this network and sent it over there with a bunch of tests in there that then SSH into the switches and verify that each connection that I've told it about is connected to the other end, that there is a connection, that routes are working, pings are happening. I could have done all that stuff if I wanted to. You could do all that stuff. You could have, like on the second day of all the kit turning up, having wired it up, you could put the configs on, run these tests, and know that everything is wired as you wanted it wired. How often have you wired the stuff to discover that it's not actually wired all that way? It happens all the time. The other thing that comes out of this is you get a really good documentation. It self-documents the network you've built. So, thank you very much.